Good morning. Happy Wednesday. Last day of new material. Get pumped. Good morning, Michael. How's it going, guys? Next week is next week usually a review for you guys? I know we have review in this class, but what about other classes? Is there new material, or is it just finishing everything up? Project is finally over. Okay, that makes sense. So, I bragged about this morning, and I know not everyone's here, but I just want to say that I opened up my grade book on Tuesday morning, and everyone had submitted the project. That is the first time, and I mean, I don't know the quality of the submissions, but this is the first time I have ever had everyone submit the project in any class that I've done. And it's just incredible. I was just so amazed. Like, it was just, I was blown out of the water this semester, and you guys as students have just raised my expectations. I don't know, it's just been great. This semester has gone way better than I ever thought it could be. What do you mean was it not accepted? No, everybody had submitted the project. Everybody had a submission. Which in the past, people just haven't done the project. They just decided not to do the project. Which, as a student, is completely your prerogative to not do an assignment. It is your grade. But this is the first time I've had everybody submit a project. Like, I've never had that before. And it was just, I had to brag about it. Because that's never happened before. Like I said, this semester is just, semester's been beyond. If we had submitted at 12:01, it would, 12:01 would have been accepted. That's not an issue. I mean, when we say no late submissions, at least for me, when I say no late submissions, like, there's a difference for me between, 12:01, 12:02, 12:10 versus like a day late or even mid next day. To be honest, if it's there when I wake up the next morning, I don't care. You did your assignment. Like, you made it in. If it's 2 minutes late, if you press the submit button and it just delayed, I don't care. It's still accepted. Not an issue. So yeah, but I just want to thank you guys for being my students. You've been great. We still have one more week, but you've been great. It's been awesome. Semester's been more than I ever could have imagined it would be. It just makes me happy. So, we're almost there. We can do it. One more week. Next week's gonna be all review. There's no new videos to watch on Friday, which is awesome. That means I don't need to create new videos. All the homework solutions and practice exam and everything will be posted by probably Saturday morning. So, yeah. Today we are going to go over eigenvalues and eigenvectors and diagonalization, so that you can finish up your last homework. Your homework, 2 days. Understandable, Squiddy. So my policy is to do my absolute best to make sure that all of your assignments that you've ever turned in are graded before the final. It's a little bit harder when the final is at the beginning of finals week, but your project should be graded. I need to enforce this I need to talk to the TAs about this. It should be graded by next week, before the end of next week. I did send out an email to the TAs on Monday about how to grade the project. So I'll send them another reminder email yesterday. But you should have all of your grades and everything done before the final. So if you are sitting there and you're wondering, okay, I have all of my grades in and now I'm curious about what I need to do on the final, I do have that spreadsheet that I posted under introductory material. I posted it somewhere, I can't remember. It's on UB Learns, that you can use to estimate your grade. You can put all your grades. You can use that to kind of play around with what you need for the final exam. So if you're really concerned, you can do that. You should have all of your grades, like I said, before the final. And it's totally understandable that you're getting the end of semesteritis. It is nicer outside. It's always the worst. So the best thing you can do to study is do your homework. So small pieces, one at a time each week, practice. That's true for pretty much most classes. Yeah, we can do it. You can do it. Mostly you. I mean, I'm also waiting for the end of semester. Like, I'm just sitting there like, okay, when are things gonna be done? When are things gonna be done? So I understand, to a point. Okay, let's go ahead and finish up. Aw, but programming's so much fun. The final is linear algebra problems. There will be a practice exam posted. It will give you a general idea about what to expect, but it's going to be linear algebra problems. You'll be writing all of your solutions on paper, or however you write them. Just like you do your homework, you'll submit them, all that fun stuff. Danny, the exam, we will not be using Respondus. It's open note, open. You can have access to your notes, book, etc. You can use MATLAB as a resource. You can't just type in your answer into MATLAB because the way the questions are phrased, you can't just do that. But like I said, we will do a review next week. We still need to finish up today. Okay, so today we are talking about eigenvectors and eigenvalues. I'm going to go over examples just like I've normally been doing. So the idea behind an eigenvector and eigenvalue. So if you think about a matrix, what we're doing is we have matrices and vectors and all that fun stuff. Space engineering student, yes, it's going to be just like the midterm. You'll have your phone back there showing your space and your screen. Yes, it will be the same way, the midterm, open note, open, all that fun stuff. You'll just be writing on paper instead of typing on the computer. Okay, so when we think about a matrix, essentially a matrix is just used to move a vector in space. So if we think about a 2D vector, if I have a 2D vector that looks like this and I multiply it by a matrix, my new result might be a vector that's over here in space, or maybe over here in space, or maybe over here in space. So 1, 2, 3. So if I take, 1, 2, and I multiply it by a matrix, it might give me this vector, or this vector, or this vector. Eigenvectors and eigenvalues are properties of matrices where sometimes we have a vector that if you multiply it by a matrix, it really just scales it. So rather, instead of it showing up somewhere else in space, it's just scaling it along the same line, maybe this way or this way. So this is described by what's called the eigenvalue problem, which states that ax equals lambda x. So x here is my eigenvector, and lambda is my eigenvalue, which is just a constant. So this idea that we take a vector times a matrix, or a matrix times a vector, and it appears as if we just scaled the vector. So if you're ever told to verify that a vector is an eigenvector of A, you just go to this equation. We're going to set up ax. So here it would look like this. And we have x. If I do that multiplication, I end up with 0, -1, -3. negative 2 plus 3 plus 3, and then 2 plus 1 plus 1. Whoop. My result ends up like this, negative 4, 4, 4. And that's the same as if I just multiplied my vector by a constant. So my original vector was negative 1, 1, negative 1, 1, yep. If I look at these two results, so here's ax, and here's lambda x, where it appears as if I just multiplied my vector by 4. So lambda here, in this instance, is 4. So it's the same as if I just said 4 times negative 1, 1. So it appears that when I did this matrix multiplication with this matrix and this vector, it's the same as if I just did 4 times negative 1, 1. And this only happens for certain vectors. It's not true for all vectors. Let me copy and paste this, and let's do this multiplication for another vector. Copy. Paste. So let's say instead of it being negative 1, 1, I had like negative 2, 4, and 3. If I did this multiplication, I would end up with 0, negative 4, negative 9, or 0 minus 4 minus 9, negative 4 plus 12 plus 9, 4 plus 4 plus 3, which would give me negative 13, 17, and 11. This is not the same as if I just multiplied my vector by a constant. Okay, so this vector appears as if I just multiplied my vector by 4, where over here, it is not the same. So that is the eigenvalue problem, where for some vectors of A, or some vectors, when I multiply A times that vector, it appears as if I just multiplied my vector by a scalar. Whereas most vectors, it does not appear that way. So lambda can be a fraction, but lambda has to apply to every single number in this vector. So it has to be 4 times every single number. For my original vector. So if I multiply this vector, negative 2, 4, 3, so it's matrix multiplication. This with this, 0 plus negative 4 plus negative 9. So the dot product between the first row, yeah, it's matrix multiplication. So notice it would seem as if I just did my vector times this vector, element by element. So as if I multiplied negative 2 by negative or 13 halves. And this one by 17 fourths, and this one by 11 thirds. But notice all of these aren't the same number. I can't multiply each value by a single constant. It does appear as if I multiplied each value by a different constant, but the idea of the eigenvector problem is that the entire vector appears to have been multiplied by a single scalar. Where over here, A times X appears as if I really only just multiplied X by 4. So here I essentially can replace A by a single scalar. That is the eigenvector or eigenvalue problem. Okay. That's great, that's fine and dandy. But how do we find eigenvalues and eigenvectors in a matrix? Okay, so let's say we have this A matrix and we are asked to find the eigenvectors and the eigenvalues of the following matrix. So we have this problem, AX equals lambda x. That's our eigenvalue problem. We're trying to find what x vectors behave as if they've just been multiplied by a scalar. If I rearrange this, I'm going to end up with that's not what I wanted. Ax minus lambda x equals 0. I just brought this to that side. If I factor out an x, it behaves like this. A minus lambda times x equals 0. And when I say a minus lambda, I'm really saying a minus lambda I equals 0. So this here is a matrix, this here is a vector, this here is a vector. So this is a system of equations. If you remember from Monday, we had this nice little flowchart that I put together. Oops, forgot to erase all that. That tells us what happens when we have a vector, or when we have a system of equations with our b vector as 0, which is what we have. We have a minus lambda I x equals 0. This is what's called a homogeneous system because our b vector is 0. This is this instance. This is our flowchart for a homogeneous system. Notice a homogeneous system is always consistent, which means there's always at least one solution. If there is a unique solution, we have this scenario, and it turns out the unique solution is always x equals 0. So I know if I plug in 0 for x, I'm going to end up with 0. I don't care about that. I know that 0 equals 0, so I don't care about that scenario. So I'm going to cross this one off. When we are trying to find eigenvalues and eigenvectors, it turns out we are forcing it to meet this box here. We're going to force it so that x is an infinite number of solutions, which means that the determinant of A has to equal 0. Okay, so that is the principle that we are playing off of. We are forcing ourselves to have an infinite number of x's, an infinite number of eigenvectors, by forcing our determinant of A to equal 0. So the way that we are going to find our eigenvalues and eigenvectors is by essentially applying these principles. So the first thing we do is we force our determinant of this matrix to have a determinant of 0. So A minus lambda I is going to have a determinant of 0. Okay, so we actually need to do this. So A minus lambda I looks like this. Lambda I is just identity with lambda along my diagonals. So when I do this math, I end up with identity subtracted from all the values in A along the diagonal. So here's A minus lambda I. And what we're going to do is we are going to force this matrix to have a determinant equal to 0. So now I need to solve for my determinant. So I'm going to do cofactor expansion along the second column. You can use whichever method you want to find the determinant. It does not matter. You know what? I'll do it the modified fish method. I'll do the modified fish method. I did cofactor expansion this morning. We'll find the same answers, right? Okay. So I just copy those values next to each other. I'm forcing my determinant to equal 0. I'm going to use my modified fish method. This tells me this diagonal is 1 minus lambda times 3 minus lambda times negative 3 minus lambda. This diagonal is 0, and this diagonal is 0. Oh, that's nice. That's fun and dandy. Okay, other way. This diagonal... Hold on. This one. Here we go. This one ends up being 0. This one ends up being 0. And this one ends up being 3 times 3 minus lambda times negative 1. Just follow that? Hopefully. So my determinant of A minus lambda I equals 0. That equation is 1 minus lambda times 3 minus lambda times negative 3 minus lambda plus 0 from these diagonals minus 0 plus 0 plus 3 times 3 minus lambda times negative 1. Set that equal to 0. And then solve for lambda. Note, when you do this, you end up with a polynomial. Specifically, if you have a 3 by 3 matrix, you're going to end up with a cubic polynomial, which means you have to factor a cubic polynomial, which is not always easy to do, not always straightforward to do. I encourage you to not simplify until you absolutely can't go anywhere else. So if I simplify, or if I take out my zeros and kind of rearrange, I'm not multiplying anything through right now, but if I just simplify this a little bit, I have 1 minus lambda, 3 minus lambda, negative 3 minus lambda, plus 0 plus 0. This ends up being negative 3 times 3 minus lambda. So I get plus 3 times 3 minus lambda equals 0. Notice I just did some basic simplification. Notice I can factor out a 3 minus lambda. So I factor out a 3 minus lambda, and that will give me one of my factors, which is great. That leaves me with 1 minus lambda times negative 3 minus lambda plus 3. I'm going to factor or FOIL this out. So I end up with negative 3 minus lambda plus 3 lambda plus lambda squared plus 3. Keep going. Keep going. Factor out a lambda, which is great. So here we go. Those are my factors for my cubic polynomial. Note, I did not simplify to have a cubic polynomial. I kept everything as factored out as possible as I could, just to make it simpler. This problem is actually easier if you do cofactor expansion along column 2, mostly because you have 2 zeros there. Also, we will not give you more than a 3 by 3 on your exam. And the problem, like, we won't give you a complicated polynomial to factor. So make sure you don't expand any more than you need to. Okay, so this means that my lambda values will be 3, 1, and negative 2. Woohoo! I found my answers. Okay, so I have 3 eigenvalues. Lambda 1 equals 3, lambda 2 equals, what was it? 0? Oops, 0, not 1. 0, and lambda 3 equals negative 2. I found my eigenvalues. So these are my constants. That's great. I found one piece of my equation. I found lambda. Now I need to find my eigenvectors. So we forced this determinant to equal to 0. That's great. Now I need to solve this system of equations for x. So what we're going to do is we're going to plug in each value of lambda into that equation and solve for x. So once we do that, it looks like this. So I'm going to start with lambda 1 equals 3. Note there are 3 different eigenvalues, which means we have to do this 3 times. Sometimes, depending on how your polynomial factors, you might end up with the same eigenvalue twice. So you might end up with a situation where you have like 3, 3, and negative 2, or negative 2, 1, and 1, or something along those lines. And that's fine. So if you have 3 distinct eigenvalues, then you have to do this 3 times. If you have 2 distinct eigenvalues, you would have to do it twice, etc. But I have 3 of them, so we're going to do it 3 times. We're going to plug in each eigenvalue into this system of equations and solve for x. Note, though, this system of equations has an infinite number of solutions. We forced it to be that way by making sure that the determinant of this matrix is equal to 0. So the way we do this is we solve it using Gauss-Jordan elimination. So if I plug in lambda of 3 into my A minus, here we go, into my equation, I get a minus 3 identity. X equals 0. So I get 1 minus 3. 3 minus 3. And negative 3 minus 3. And I'm going to write my augmented matrix right away because my B vector is just a bunch of zeros. So I just subtract 3 from all the elements along my diagonal, just like I did with lambda up here. I just plug 3 in to here. When I simplify that, this is the equation I'm solving. Note you end up with your column, a column of zeros here. That's fine. Whatever you end up with, keep moving forward. That's not a problem. The thing is with these, when we are finding our eigenvectors, we know we're going to end up with an infinite number of solutions. So our RREF, our reduced row echelon form matrix, typically looks a little bit weird, a little bit different from what we're used to. So for example, if I do this one, I'm going to do Gauss-Jordan elimination. So I'm going to start by making these 2 zeros. So I'm going to say row 2 equals 5 times row 1 minus 2 times row 2. And I'm going to say row 3 equals row 2 times row 3 plus minus row 1. So when I do that, row 1 stays the same. And row 2 ends up being, okay, row 1 times 5 is negative 10, 0, 15. Row 2 times negative 2 ends up being 10, 0, 4. So I get 0, 0, and 19. And then row 3 ends up being row 1 times negative 1. And row 3... row 3 times 2 is negative 2, 0, negative 12. So it ends up being 0, 0, negative 15, right? Something along those lines. If I divide this one by 19, divide this one by negative 15, I end up with a 1 here and a 1 here. If you're doing this on your exam, show all your steps. Write those out as individual row operations. So what I can do, my last set of row operations, I want to make this a 0 and this a 0. So I'm going to say row 1 equals row 1 minus 3 times row 2, and row 3 equals row 3 minus row 1, or row 2. So this becomes negative 2, 0, 0. This becomes 0, 0, 1, 0, 0, 0. Note I end up with my row of zeros at the bottom. I want that to show up. If you do not end up with a row of zeros, it means you did it wrong. And I can divide this by negative 2. So my final result ends up looking like this. Which is different from what we've seen. This one looks a little weird. So write your system of equations here. This doesn't say that 1 equals 0. This says that x1 equals 0. This says that x3 equals 0. So remember, this first column corresponds to x1, this second column corresponds to x2, this third column corresponds to x3. So whatever you end up with, you still want to write your system of equations that shows up. We know x1 equals 0, we know x3 equals 0. We have no information about x2, which means that it's a free parameter. That x2 is anything we can choose it to be. So when you're finding your eigenvectors, what you're really finding is a whole bunch of vectors. You're finding an infinite number of solutions, an infinite number of vectors. So if I wrote this as a vector, it would be 0, t, 0, where this t here is just my free parameter. And in reality, you can choose t to be anything you want. Typically, typically we write our eigenvectors by picking one of these. So we typically pick the one with the smallest whole numbers. So I would technically write this as 0, 1, 0, where this is my eigenvector for my eigenvalue. And it can be any one you want, any scalar multiple of this. You can pick t to be whatever you want. You can pick it to be, except for 0. You probably shouldn't choose 0. You don't really care about the 0 vector because 0 equals 0. We know that. But you can choose it to be whatever you want. 1, 2, 3, 4, 1/2, 1/3, 1/100th, whatever you want it to be. So for this eigenvalue, for lambda 1 equals 3, my corresponding eigenvector is 0, 1, 0. That's my process. So then we repeat for our next one. So I need more space. Give me space. Give me space. Come on. Enter. Okay. So now I'll repeat for lambda 2 equals 0. I'm going to plug it in. A minus 0i x equals 0. So now it's going to be 1 minus 0, 3 minus 0, negative 3 minus 0. And then my b vector is zeros. So I subtract 0 from all the elements along the diagonal. And then I solve my system using Gauss-Jordan elimination. So make these zeros. So I'm going to say row 2 equals row 2 minus 5, or plus row 5 times row 1. Row 3 equals row 3 plus row 1. So 5 times row 1 is 5, 0, 15. So row 1 doesn't change. Row 2 becomes 0, 3, 13. And row 3 becomes 1 plus negative 1, which is 0, 0 plus 0, which is 0, 3 plus negative 3, which is 0, and 0. I get my row of zeros. And it's exciting because that's what I expect. If I didn't get that, I would have done it wrong. So a lot of times, since we only give you 3x3s for eigenvalues, well, no, I shouldn't say only, but if you're finding the eigenvectors, typically we're only giving you 3x3s. So you can see that since you end up with your row of zeros, you typically don't need to do that many row operations. This one's nice because there's already a 0 here and here. I'm almost in Gauss eliminate or in RREF. I just need to divide this by 3. So my final matrix ends up looking like this. So there we go. Write my system of equations. This one says x1 plus 3x3 equals 0, or that x1 equals negative 3x3. This one says that x2 plus 13 thirds x3 equals 0, or that x2 equals 13 thirds, negative 13 thirds x3. x3, I have no information about it. That means it's my free parameter. Yes, Flora, you have to divide by 3. Technically, this is RREF. I mean, in order to technically get RREF, no, you do not have to divide by 3. But that will show up when you solve for your system of equations here. So I guess you don't really have to. If you do look at this though, you cannot get any more zeros. You can't make this a 0, because if you tried to add these two rows together, you would make that a non-zero. You can't make this a 0, because if you added these two rows together, you would make that a non-zero. So you just keep finding as many zeros as you can until you can't move forward anymore. That is essentially how you find RREF. And then technically for RREF, we want our pivots to have 1s, so that's why I divided by 3. But as Flora mentioned, unless you are told to explicitly find RREF, you don't really need to divide by 3 because it will show up when you solve your system of equations. So if I wrote this set of vectors arbitrarily, it would be negative 3t, 13, negative 13 thirds t, and t. Where t here is my x3, it's my free parameter. Typically though, what we're gonna do is we pick one of these vectors. We pick the one that gives us the smallest whole numbers, and you don't have to. You can pick whatever value for t you want. You could pick t as 1, which means x1 would be negative 3, which means x2 would be negative 13 thirds. I am going to pick t so that I end up with whole numbers, and I'm going to pick t to be negative 3, which means that x2 here is going to be 13 and x1 would be 9. So here is one of my eigenvectors for my eigenvalue of 0. But it's really any scalar multiple of this. So x2 equals 0. My eigenvector was 9, 13, and negative 3, I think. Yes. There we go. I found my second set. Woohoo! And then I do it for the third one. So I have lambda 3 is equal to negative 2. So I plug it in. A minus negative 2i, x equals 0. Solve my system of equations. So I have 1 plus 2. Negative 3, or positive 3 plus 2. 3, negative 2. Negative 3 plus 2. My b vector. I get 3, 0, negative 3, negative 5, 5, negative 2, negative 1, 0, negative 1, 0, 0, 0. Start solving my system. Row 2 equals, and I mean, you can rearrange these in any way you want. If you want to do row swaps first, it doesn't matter. It's Gauss-Jordan elimination. You have free reign over all your row operations. So I'm going to say row 2 equals 3 times row 2 plus 5 times row 1. And row 3 equals 3 times row 3 plus row 1. So row 1 doesn't change. That's a positive 3. Don't worry where that negative came from. Thought it was weird. So, you know what? Scratch that. I'm going to divide row 1 by 3 right away. So I end up with 1, 0, 1. It'll just make my row operations easier. Now, I can say row 2 equals row 2 plus 5 row 1, and row 3 equals row 3 plus row 1. So 5 row 1 is 0, 5, 0, 5, 0, 5, 0, negative 5, 5, negative 2, 0. So row 1 doesn't change. Row 2 becomes 0, 5, 3, 0, and row 3 becomes 0. Which is great, because that's what I want. I can divide by 5. I will demonstrate that you don't technically have to. So this tells you that x1 minus x3 equals 0 plus x3 equals 0, which tells you x1 equals negative x3. This one tells you that 5x2 plus 3x3 equals 0, or that x2 equals negative 3x3 over 5. x3, there's no information, so it's your free parameter. So no, we did not divide this one by 5. So we didn't technically get to RREF, but whatever. It still showed up over here. So as a vector, this is negative x3, negative 3/5 x3, x3. I'm going to choose x3 to be, or I'll draw it as t, like I did. I'll choose t to be 5, so that means this one is negative 3 and this is negative 5. There we go. So when lambda 3 equals negative 2, x3 is negative 5, negative 3, 5. Woohoo! Okay, let's verify our answers with MATLAB. Sorry about that. There's my nice royalty-free playlist. Okay, so if we want to verify our answers with MATLAB, you may have guessed, we start plugging things into MATLAB. A equals 1, 0, 3, negative 5, 3, negative 2, negative 1, 0, negative 3. If you want to check for your eigenvectors, you can use the EIG function. So EIG, short for eigenvalues. So, okay, let me rephrase that. If you want to check for your eigenvalues, you use the EIG function. And note, it gives us my eigenvalues. 3, 0, negative 2, which I got there. So that matches what we found. Woohoo, we did that right. Perfect. If we want to check for our eigenvectors, remember, when we do our eigenvectors, we get an infinite number of solutions. There is no easy way to find an infinite number of solutions on MATLAB. We can use the RREF function by plugging in a minus our eigenvalue, 3 times I, 3 next to zeros, 3 comma 1. And it will give us our RREF form. Notice that matches what we found for our first eigenvalue, or for our first eigenvector, but it's not going to give us a vector. It'll give you your RREF, and you would have to interpret the same as if you found it on paper. But what we can do is we can confirm that if I take x1 and multiply it by a, it appears as if I just multiply it by 3. So I'm going to plug in x1. x1 equals 0, 1, 0. If I take a times x1, voila, it works. It appears as if I just multiplied x1 by 3. So if we want to check our second eigenvector, we can do the same thing. We can plug in x2. So x2 ends up being 9, 13, negative 3. And this is magic. A times x2, zeros! Which makes sense because our eigenvalue is 0. So we should get zeros. It's just like crazy. Like I never would have thought that a times this vector would give me a bunch of zeros, but it does. It works. It's weird. Like you're like, oh, okay, 0 once. That's fine. That's not abnormal. But 0 3 times. It's like magic. Okay, so we've checked our second one. And then we can check our third one. Same process. So x3 was equal to negative 5, negative 3, and 5. So if I do a times x3, it appears as if I've just multiplied it by negative 2. This one's also magic. It's just more exciting when it's a bunch of zeros, because it's like, what? It worked. Okay. That is how we can find all of the eigenvalues and eigenvectors given a matrix. Notice that's a long process. That is a long process. But keep in mind, we are working off of the fact that we have the equation a minus lambda I x equals 0, which is derived from ax equals lambda x. So if you're given any piece of these, if you're given lambda, if you're given x, decide which one, what pieces are you given, where are you trying to find out? What are you trying to find out? If you're given lambda and you need to find x, you need to use this equation, the second one. If you're given x and you're asked to find lambda, then you can use the first one. So it depends on what piece of information you're given. What are you trying to find? If you're just given a and you're told to find both, then we need to force a minus lambda I, the determinant to be equal 0. This is called your characteristic equation. I forgot to mention that. It's called the characteristic equation. You use the characteristic equation to find your lambdas, and then you can plug each of those in to this system of equations to find your x's. It's a long process from start to finish, depending on what a looks like. But once again, you might be given pieces of that. That might make it easier. Okay, let's do one more problem. Here we go. I'm gonna enter a couple more times. Let's say we are told to find the diagonalization of A, given A and its eigenvectors. So diagonalization, it's similar to how we can break up A into L and U, or PL and U, where we have a lower triangle matrix and an upper triangle matrix. Diagonalization of a matrix is what's called decoupling a system. And there's properties associated with it. We're not going to go into that, but I will show you how to do the diagonalization. Okay, so in order to do the diagonalization of a matrix, we need to know the eigenvalues and the eigenvectors. We are given A and its eigenvectors. I need to find lambda. If you're ever given the eigenvectors, we can easily find lambda by just plugging it in here. So I'm going to take A, multiply it by each of my vectors. So matrix multiplication, I have 1 times -1 plus 4 times 0 plus -5 times 0, so -1 plus 0 plus 0. Then I have 0 plus 0 plus 0, then 0 plus 0 plus 0. This is nice, there's lots of zeros. It ends up being -1, 0, 0. So it appears as if I've just multiplied my vector by -1. So that means my first eigenvalue is -1. First eigenvalue, first eigenvector. Do that for my next one. I'm just going to copy and paste this. Copy. Paste. My second eigenvector was 5, 0, 4. So I do my matrix multiplication, which gives me -5 plus 0 minus 20. Plus 0 plus 0 plus 0, that's convenient, plus 0 plus 0 plus -20. So I get -25, 0, and -20. So it appears as if I've just multiplied this vector by -5. So lambda 2 is -5. And then the same thing for my last vector. My last vector looks like this, 1, 1, 1. Do that multiplication, I end up with -1 plus 4 plus -5, 0 minus 2 plus 0, 0 plus 3 plus -5. When I add all that beauty together, I end up with -2, -2, -2. So it appears as if I've just multiplied this vector by -2. So lambda 3 is -2. Okay, there we go. I have my 3 eigenvectors. I have my 3 corresponding eigenvalues. So anytime you're doing a diagonalization and you find your eigenvalues, you need to stop and pause. Because we can only have a diagonalization of a matrix when we have 3 distinct eigenvalues. That is very important. If I ended up with lambda 1 equals 3, lambda 2 equals 2, and lambda 3 equals 2, I cannot do a diagonalization with that. You have to have 3 distinct eigenvalues. So since I have -1, -5, and 2, I can do the diagonalization of A. So in order to do diagonalization, we need our eigenvalues and our eigenvectors. Once we have those pieces, then it's pretty simple. So the diagonalization of A can be written as x inverse times A times x equals capital lambda. So that's capital lambda. We typically see lowercase lambda. Capital lambda looks like a little tint. A is just A. X is a matrix that's going to be filled with my eigenvectors. So here are my 3 eigenvectors. So to create X, I just place them in as columns, and it doesn't matter the order. So I'll do column 1 is X1, column 2 is going to be X2, and column 3 is going to be X3. So there's X. It's just filled with my eigenvectors, just as columns. And then X inverse, you may have guessed, is the inverse of X. So I can use MATLAB in order to do that. So go back to MATLAB. And I mean, we know how to do this on paper. We know how to find the inverse now. If you're asked to do it on paper, you can use Gauss-Jordan elimination. In order to find the inverse, you can use your cofactor. Your cofactors find the inverse. It doesn't matter. If you're told you can use MATLAB, you can use MATLAB. So xi equals inverse of x. There we go. There's my inverse. I feel like it looked different this morning. 1, 0, -1, 0, -1/4, 1/4, 0, 1, 0. I typed in x wrong. That's why it looks weird. X is 1, 5, 1, 0, 0, 1. There we go. There we go. That looks better. So whenever you're typing things in, make sure you do it right. -5/4, -1/4, 1/4, 1, 0. Okay, there we go. There's X inverse. Thank you, Ryan. Okay, back to just the notes. Okay, so we have X inverse, we have A, we have X. Lambda ends up being, you know what? We'll just do it in MATLAB. Okay, so let's do this multiplication. So I have X in there, I have X inverse A. I do not have in there, so let me type in A. A is -1, 4, -5, 0, -2, 0, 0, 3, -5. Okay, so I have A, I have X, and I have XI. I'm going to do this multiplication. The order matters. So XI times A times X. And if I did it right, which I did, this is what we get. My answer ends up being -1, 0, 0, 0, -5, 0, 0, 0, -2. If we go back to our paper, notice the values that show up in lambda are my eigenvalues. So if I do this multiplication, I end up with a diagonal matrix where the diagonal contains my eigenvalues. This first eigenvalue, or this first column, this first number is lambda 1. This second number is lambda 2, and this third number is lambda 3. Crazy! And that order matters. It's lambda 1 here because I have x1 here. It's lambda 2 here because I have x2 here. And it's lambda 3 here because I have x3 here. If I had written x in a different order, if I had written x as 1, 1, 1, 5, 0, 4, 1, 0, 0, where I had written x3, x2, x1, then lambda would be the same numbers, but also in the same order, or in this same order here. It would be x3. No, it would be lambda 3, lambda 2, lambda 1. So the order of my eigenvectors, or my eigenvalues along the diagonal, matches the order in which I put my eigenvectors in X. And yes, Danny, it will always be zeros beside the diagonals. So this always ends up being a diagonal matrix where I have zeros here, with my eigenvalues along the diagonal. Yeah, so Jalen, yes. I wouldn't necessarily ask you to show this matrix multiplication. That's a lot of operations to show. You should know, though, how to put together X and put together lambda without doing any calculations. Sometimes we might show you how to find the inverse of X, sometimes not. But, I mean, that's just finding the inverse of X. But you need to know how to put together your X, and you need to know how to put together your lambda. Which, if you put in your X, your eigenvectors, just that same order goes along the diagonal. So unless it says show the matrix multiplication in order to find lambda, you can just know that if x looks like this, a looks like this, lambda will look like that. That's just how it works, which is pretty awesome. I'm not gonna lie. I find it exciting that it works out mathematically like that. But there you go. That is our last material. So we went over a lot today. How do we find the eigenvalues? We use our characteristic equation. We force a minus lambda I to be equal to 0. We end up with a cubic polynomial for a 3x3. Keep in mind, don't simplify or don't expand unless you absolutely need to. You can use that to solve for your eigenvalues. Once you have your eigenvalues, you plug each of them in to this system of equations and solve for your eigenvector or your family of eigenvectors using Gauss-Jordan elimination. You need to end up with that row of zeros because we're expecting an infinite number of solutions. Pick one of your solutions. Typically, we pick the one with the smallest whole numbers, but to be honest, you can pick whichever one you want. Do that for as many number of eigenvalues as you have. If those eigenvalues are distinct, then we can also write the diagonalization of A, where we find our eigenvalues, we find our eigenvectors, we write out A, which A is the same. X is filled with our eigenvectors that we found. And then lambda ends up being our eigenvalues on the diagonal. Okay. The order matches. So if it's x1, x2, x3, then we do lambda 1, lambda 2, lambda 3. If it's x2, x3, x1, we do lambda 2, lambda 3, lambda 1. Okay, that's it. That's it. Benny, I mean, those steps are listed out so the steps are listed out in the notes. There's also PDFs of examples worked out that are posted on UB Learns as well. Go to those. Those should help. There's also some videos as well posted there. AP, yes, your lowest homework is dropped. So anything you see on UB Learns with everything graded, that is the lowest your grade would be. With your lowest homework drop, it will increase your grade. And next week we do have live lectures on Monday and Wednesday still. They will be exam review. I will post the practice exam hopefully by Friday. It's almost done, I think. I wasn't in charge of putting that one together, so it should be almost done. So I will post that as soon as possible. The best thing you can do for studying right now is to do your homework. So make sure you do your homework, get that done, and then you can move on to the practice exam and keep moving forward. But next week we do have live lecture if you want to come. I mean, you don't ever have to come to lecture, but I will be doing a live lecture, come or not come. I appreciate when you guys come. I like your questions. But I will be doing practice problems, all of that fun stuff. And yeah, that's it. So any final questions? If not, I will see you guys next week. Have a great day, great rest of the week.